Hi, my name is Gene Schrader, AE8GS, and this video is about my experiences building a semi-stealthy fan vertical antenna. I'm a new ham and this is my first antenna. I want to first say that there's nothing terribly special about this antenna or how I built it. It's a well-known design and it's similar to popular antennas you can buy like the DX Commander. The main difference is that I built it from scratch and I built it so it's not very visible. This is what people call a compromise antenna because it's not how you would build your antenna in an ideal world. In other words, you have to make compromises based on your situation. In my case, I live in a condo, so I can't install anything very visible like a mast or a tower. So you do what you have to do and you see how well it works. This is what I did and that's what this video is about. Now, even though my antenna might not apply to you, you might find this video useful to see the process I went through, and it might give you some ideas on what you might do building your antenna, whether it needs to be stealthy or not.
So here's an outline of this video. I'll go through this briefly. First, I show you what I had to work with. So this will be the back of my condo and my backyard. Then I discussed some antenna alternatives I considered. My goal was to start with something that would be cheap and easy to prototype, and if that didn't work, I'd go to plan B. Then I discussed the process of building and testing my prototype antenna. As you will see, it's really crude, but it was good enough for testing. I used a nanoVNA and I used Whisper digital mode to do some on-the-air testing. Since I was happy with the performance of the prototype, I went on to what I call a semi-permanent build and added elements for multi-band operation. Finally, I talk about some future enhancements. So that's the outline, and let's get started. Here is the back of my house, which is a condo. This is what I have to work with. As you shall soon see, it's built on a hillside, so the lower level you see here is actually a walkout basement, and the main floor is above that. The house is wood construction with wood siding. Being in a condo, I can't erect an antenna that is visible in any real way, and so that limits what I can do. But I like living here, and that's part of the deal. And frankly, I'm fine with a modest antenna as long as I can get a signal out and make contacts, and I'd like to do at least some DX. Now on the back of my house you can see a raised deck on the main floor and some screened-in porches with metal window screens. There are rain gutters on the eaves of the roof and some downspouts. There are also some bird feeders along the railing. By the way, my antenna is in this picture in plain sight, but kind of hard to see, and we'll get to that later. So let's pan over and you'll see my tiny backyard. I don't know how much this shows on the video, but where the lawn ends, it's a pretty steep drop-off. From the ground behind my house to the road below, it drops about 60 feet or 19 meters. The ground continues to drop off on the other side of the road, so that the total drop is about 85 feet or 26 meters. Being up on a hill helps me for sure, but this hillside is also wooded, and this will fill in with leaves in the spring. I haven't experienced that yet, but we'll have to see what it does to propagation. Here are some stealth antenna alternatives I considered. The first is to use the attic. Many people do that, and it's nice because it's completely invisible and is protected from the weather. A disadvantage is that there is significant signal loss in passing through the wall or roof of the house. I experienced that with TV antennas. Another difficulty is that working in an attic, at least mine, is not fun. There is insulation everywhere and you have to maneuver around trusses. It also gets very hot in the summer. Another possibility is to use your rain gutters or downspouts as your antenna. It's a great idea and it's easy to build and very stealthy. It is intriguing, but I think this solution is sort of hit or miss, and you don't necessarily have an idea of what's going on. But it is definitely something I would like to experiment with. Next, there are end-fed wire antennas that would connect from my house to a tree behind my backyard. This is a popular antenna, and it's well understood. I would need a matching circuit and probably an antenna tuner near where it connects to the house. Due to the terrain, the way the ground drops off behind my house, I would have to mount it very high in a tree. Also, that tree would be in community common property, which I'd like to avoid. Finally, there are vertical wire antennas with radials. Now, a vertical wire just by itself is fairly stealthy, but you need something to hold it up. A mast simply isn't possible for me. I could use a tree to support it, but with some of the same issues as I already mentioned. I could use my house to support it, but being close to the house is going to affect propagation in some way. So what did I do? Well, I decided to try a vertical wire first. And to be precise, this is a ground level, quarter wavelength vertical with ground radials. The nice thing is that it has fairly low visibility and a small footprint on the ground. The other thing is that testing of a prototype resonant vertical should be cheap and easy. I can connect it straight to my rig with no matching circuits. My rig does have an internal antenna tuner, but I shouldn't really need it. The question is, what bands can I support? Well, the distance from the roof to the ground is about 5.2 meters. Now, in theory, for the 20-meter band, I need 5.3 meters. But there is this thing called velocity factor, and it means that signals pass more slowly in wire compared to air. So hopefully, my vertical will be long enough for 20 meters, and that means I should also be able to do 15 and 10 meters. The antenna base will sit in a garden area that fortunately contains tall ground cover, pachysandra, and my wife wasn't bothered by having a small amount of kit in there. The verticals can support multibands that I'll discuss shortly. The risk factors of this choice are mainly how the house will affect the tuning and propagation. I was worried that maybe the vertical wire will have to be longer, or maybe the window screens will absorb all the signal. This is what I need to find out. Thinking ahead a little bit, I wanted to consider my options for getting multiband operation with the vertical. A simple vertical will work on the natural resonant frequency and then odd multiples of that frequency. So a vertical antenna that is resonant on, say, 14 megahertz will also be resonant on 42 megahertz and 70 megahertz, which turn out not to be useful for amateur radio. But there are different techniques for multiband, and I want to consider a few of them here. One technique is that you forget about making your antenna resonant, and instead you put a tuner right at the base of the antenna, which matches it to whatever frequency you are using. A good friend of mine has one of these, although his vertical uses a mast that is much taller than I am looking at. It is 43 feet or about 13 meters, and it can cover all of HF. Of course, it will perform much better than what I will be building. You can also use traps to get multiband operation. A trap is a coil of wire that blocks signals above a certain frequency. I won't go into detail as to how these antennas work, but for the example shown here, this antenna will appear to have 3 different lengths depending on the frequency. And so it will either have just this length or these 2 together or all 3 of them. So it could support 3 bands. The key is that it is a resonant antenna that doesn't require a tuner. But you do need to have these trap coils, and they do cause some power loss. Finally, we have a fan vertical, where you have different length elements for different bands. It is always surprising to me that these work. I would think this would be a dog's breakfast as far as resonance goes. But they work, and they are resonant and don't need a tuner. Now, as the title of this video states, I chose this last option of a fan vertical. So here's the plan. It's pretty simple. I'll build and install a prototype for 20 meters. I'll tune that antenna for resonance using nanoVNA. I'll do some operational tests of the antenna using WSPR and maybe FT8. If all goes well, I'll build a proper base fixture that supports multiple vertical radiators, the fan. I'll install some radials, burying them underground. I'll install the base fixture and the vertical radiator elements for 10 meters, 15 meters, and 20 meters. And then I'll tune the 3 elements together to deal with any interaction. I don't really know how much interaction there'll be between those different elements. At that point, the antenna is essentially done, and I'm ready to go. Now I'll show you the prototype I used for basic testing. The goal here was something cheap and easy, so it's pretty crude. The idea is that if it doesn't work well, I won't have much time or money invested and I can try something else. So for the prototype, I need a vertical wire and radials. I need to connect them to the coax that leads back to my nanoVNA or my rig. That's really it. So here it is. I used a brass bus bar that has a lot of screw terminals to connect to my radials. These bus bars are normally used, I believe, for electrical panels, and they are fairly easy to find and cheap. Then I need an SO239 connector for connecting to a coax cable. Now I could have just stripped the end of the coax cable and directly connected it to the radials and the vertical element, but this is a little nicer to work with. So I tinned all of the radial wires with solder and connected them to the bus bar. As far as the number of radials and the length, I'll talk about that later on. For the ground signal, I just made a little jumper that went from the bus bar, and at the end here it has a fork terminal that I could mount to the SO239 with a mounting screw. And I soldered the vertical element directly to the SO239 center pin. The initial length of that wire was simply the distance from my roof eave to the ground. So over here you see a little diagram of how it was set up. I mainly just loosely placed the radial wires on the ground, roughly in a circle, and I hung the vertical element on the roof. Now I did attach a wood block to my house to hold that vertical element a few inches away from this gutter right here. There's also a piece of metal that runs down the edge of the roof, and I wanted to stay away from that as well. I don't know how big an issue this stuff was, but I wanted to do what I could. Now in this picture, I show a dog bone insulator. In fact, when I first did this, I connected the vertical wire directly to a screw eye on that wood block because I wanted to have that conductor as long as possible when I started tuning. Here is just another picture of my prototype that shows everything together. So here is the bus bar, here are the radials, here is the vertical element connected to the eave of my roof, shown with a dog bone insulator, although I didn't have that until I tuned it. And then finally, here is the coax that went back to my radio desk, which I either connected to a nanoVNA or connected to my rig. I used a nanoVNA to tune the antenna, and here's how I set it up. This is not a tutorial on how to use a nanoVNA, and you can find a lot of those on YouTube. So just as a summary, for tuning antennas, the key measurements are impedance and SWR for the frequencies you'll be using. The idea is to trim the antenna so that it resonates at the operating frequency to get the maximum radiated power out of the antenna. Now when you use a nanoVNA, there's a couple different ways you can do it. One way is to directly use the device with its own touchscreen. The other way is to use a computer where you connect it to the nanoVNA with a USB cable, and you use software that runs on your computer. In that case, you don't use the nanoVNA touchscreen. And there are a couple software applications you can use. These are two that I'm aware of, and I in particular use this first one. There are probably other applications. So I like to use the computer method for a couple reasons. One, you can keep as many calibrations as you want because they're stored as files. You can also save the results in CSV files. You can take screenshots and so forth. You can also have up to 1024 sample points versus I think 201 when you're using the device directly. Having 1024 sample points allows detailed scans over a wider frequency range. And I just like using a computer and mouse and screen rather than the small touch screen. So when you use a nanoVNA, you have to decide your calibration point. This is the reference point for your measurements. In my case, I chose the end of the coax cable down here. And by doing that, I eliminate the effects of this coax and connectors when doing my measurements. Now, frankly, if I would have calibrated it here at the end of this blue coax cable, I probably would have ended up with the same tuning. It would be an interesting thing to look at. And I note here that when I was doing this work with the prototype, I just had the coax fed through door openings because I wasn't yet ready to commit to using this antenna. Now it's run through the wall. Here's a screenshot of the nanoVNA QT software for my prototype antenna. First, I wanted to show you the sweep parameters, and they go from 10 megahertz to 16 megahertz. and 1,024 sample points in between. Keep in mind the prototype antenna is for 20 meters, which is 14 to 14.3 megahertz. So I cover that and quite a bit more. So the software has two views of the measurements. There is a Smith chart view and a line graph view. So I'm going to focus on the line graph view first. On this graph, I've added actually some green vertical bars that show you the 14 or the 20 meter band. These bars are drawn by me on the slide. They aren't drawn by the software. So this is where we want to focus. And you can see on the top here, you choose the measurements you want to view. And I chose SWR and impedance. There's another measurement called return loss that people like, and I would like to add that one, but you can only choose two. I can tell you if it was on there, it is a similar shape, but it provides information in a slightly different way. So this impedance curve gives you an idea of where the antenna resonates, and the SWR curve shows how well it matches to a 50 ohm transmission line. Normally these curves line up fairly well, like you see here. So if you want, you can study antenna and transmission line theory and understand in more detail of exactly what these curves measure and why they don't quite line up. Actually, looking at the Smith chart would give you insight into that. Generally though, you just go for a minimum. Now, I didn't think to take a screenshot when I first hooked up my prototype, but these minimums were further to the left. They were too low in frequency. That was a relief to me because it meant I needed to shorten the vertical element, not lengthen it. Having to lengthen it would have been a problem for me. So I shortened the vertical element bit by bit to move the resonant frequency to the right and closer to the middle of the 20 meter band. I didn't go quite all the way because I didn't know what was going to happen when I added those elements for 10 and 15 meters. So this software allows you to put markers on the curve, and here they are. I have markers for the boundaries of 20 meters, 14 and 14.3. It displays these markers on the charts, although I don't see them exactly on the Smith chart. They also show numerically the values at that point of the measurements. And so this shows the SWR of being 1.3 to 1.5. Which is good enough for me. And it also shows the impedance of being from 66 to 69 ohms. That's higher than I would have liked, and we'll talk about that later. And I'll just add a few words about the Smith chart. The blue line shows how the impedance of the antenna varies as the frequency varies. By looking at this, you can determine the impedance of the antenna and you can determine the SWR. Some Smith charts have more, I'll say more lines on them to help you find more information. The middle point right here, the Smith chart, is 50 ohms. That would represent a perfect match. You can see our antenna doesn't go through that point. Which we know because our SWR doesn't get down to 1, but it shows that we get this close. I learned about Smith charts many, many years ago, and in those days you would use Smith charts to design matching networks using graphical techniques. I don't know if anyone does that anymore, but people still like Smith charts because it's another way of looking at the data. So now I had my antenna tuned and I was ready to try it out. I had never transmitted before, and I decided to start with digital to make it simple. So I loaded WSJT-X on my computer. I hooked up my rig to my computer. I have an ICOM 7300, so it's just a USB cable. As you may know, WSPR is a digital protocol that is not for making contacts, but rather to see where your signal is being heard. So it's a great test tool. There are listening stations all over the world. There is this website, whispernet.org, that shows you the results almost immediately after the transmission ends. In other words, the listening stations update this website. Officially, WSPR showed I was transmitting at 10 watts, but it might have been 20 watts and I didn't fill out the WSPR GUI correctly. Anyhow, when I saw my results, they were in tabular form, not a map like this. but I was thrilled to see it. I was getting to Europe, Africa, South America, Antarctica, Australia. It was clear that this antenna was getting my signal out, and so I decided to go forward with it. That same day, I did a little FT8, made a few contacts in the US. I think I did one in Cuba. So that was looking good as well. I'll say digital modes are a great way to get started and to test out your equipment. Although since then, I found I like sideband and conversational digital modes better. The rest of this video is going from a crude prototype to what I call a more permanent version, not necessarily the final version. The first thing I want to do is show you the parts I used and where I got them. I won't go through this list in detail. You can pause the video if you wish. I'll just cover a few highlights. For both the vertical elements and the radials, I bought wire from DX Engineering that is sold for both purposes. It is fairly heavy, 14 gauge, and it has UV resistant black insulation. I decided to continue to use these bus bars for my radials. You can get a nice radial plate from DX Engineering, but it's a lot more expensive and I'm not sure I need it. Maybe I'll decide in a year or so that I need it. For the vertical elements, I also use bus bars, but of course they need to be insulated from ground, and so I found these on Amazon that have these little insulating stands. So that's it for parts. Now for radial design. This is a complex subject and I spent a lot of time reading about it. I want to mention up front that the design of radials for ground level verticals is much different from elevated verticals like you would see for 2 meters. These antennas, like for 2 meters, are often called ground plane antennas. Next, I want to talk about the ideal case versus reality when it comes to vertical antennas and radials. An ideal vertical antenna would have a perfectly conducting infinite ground plane. The return RF current is carried on this ground plane. A real vertical antenna uses the earth, plus a finite number of radial wires or other types of conductors. These wires are known as a counterpoise and are needed because the earth is not a great conductor and will have power loss. An ideal vertical antenna has an impedance of 36 ohms. That 36 ohms is not a physical resistance, it is a conceptual resistance that is used to account for the power being radiated. A real vertical antenna has the radiation resistance plus an additional ground loss resistance which is used to account for the power lost in the ground. Thus, its overall impedance is going to be greater than 36 ohms. The number and the length of radials, as I mentioned, is a complex and well-studied topic. N6LF has done a lot of theoretical and experimental studies on radials. Here is his website, and I encourage you to read some of these papers. Generally, more and longer radials reduces ground loss resistance and improves the efficiency of the antenna. Experiments show that radials should generally be at least 1/8 wavelength of the longest wavelength you're using. Some people like a quarter wavelength, but there are diminishing returns as you go longer with your radials. Generally, the more wire you use for radials, the better. So if your radials have to be short, you should just put more of them in. So now let's get down to the reality of my radials. The first problem I had is that some of the area near the base of my antenna is covered by the house or a sidewalk, so I can't put radials there. You just have to do what you can do. In the end, I installed 8 radials, which is less than ideal. I think I could install about 4 more, and I may do that this year. I spent a lot of time deciding on the length, and I ended up making them about 3.9 meters long. This is between 1/8 and 1/4 wavelength for 20 meters. Now for installation over lawns, radials can be stapled down with these staples you can buy at a garden center, and over time they'll become embedded in the grass. For my project, where I don't mow the lawn, I wanted to be 100% certain that the radials would not interfere with lawn care, so I buried them. I buried them about 2 inches deep or about 5 centimeters. Burying radials to a reasonable depth has no effect on their operation. And burying radials is typically done by slicing the soil with a spade and pushing the wire in the gap. So here's a spade, and if you can see, there's a little gap there, and you shove the radial down in there as you go along. When I did it, the ground was fairly soft, so it wasn't too hard. Now I needed something a little more substantial for the base of my antenna. As you might remember, for the prototype I just had pieces and wires lying on the ground. So I used some aluminum stock I got from a home center and sort of made it up as I went. My objectives were to make it cheap and expandable for more vertical elements and radials. You'll see some pictures of how it looks installed in just a minute, but here is the idea. I used this angle aluminum for the base. It's about 12 inches long or 30 centimeters. And there are two holes here for spikes, lawn spikes, to hold it in place. You can see this bus bar attached to the bottom where the radials are connected. There's this insulated bus bar up here for the vertical elements, and I raise it up a little bit so it wouldn't get into contact with the ground. And just above that is the SO239 connector. I'll describe this more when we get to the pictures. Here I show the vertical elements. Now these are really hard to see in photos, so I added these thick colored lines on the slide so you could see them. You can see how they are mounted on the roof eave and on the outside of the deck railing. I used some wood blocks in all cases to keep them away from the wood, just a small amount. As you can see, I need to paint all those blocks here, and here. In each vertical, I use a dog bone insulator, like here's one. On the one end is the actual wire, and I just loop it through the insulator and I fasten it with tie wraps. On the top end is some string which attaches to a screw eye on the wood block. Now these just need to support the weight of the wire plus any wind loading, which isn't really that high. You'll notice I have a temporary vertical, I call it temporary, for 6 meters. I wanted to get on a local 6-meter net, and I added that vertical and tuned it in about 30 minutes. It probably isn't a very good antenna for 6 meters, but it worked for me. So here are some photos of the ground fixture at the base of the antenna. As you might remember, it sits in a little garden that has ground cover Pachysandra growing in it. So on these fixtures, the vertical elements simply hang down, and there's not much wind loading, so I just stabilize them with some dog bone insulators that are also fastened to the base fixture. There are 2 short wires that go from the radial bus bar up to the SO239 connector because I wanted a solid ground connection there. I did use some gel or paste that is meant to prevent corrosion when joining dissimilar metals like brass and aluminum. So for instance, I used it where I mounted this bus bar here to the aluminum. I don't know if that's really that necessary or whether it's really very effective, but it's something I did. And I still would like to have some sort of solution to keeping rain off of the vertical elements and the SO239 connector. Right now it's exposed to the elements. And this picture is just the same thing. You can see how the coax connects to it. So in this picture I show how the fixture is attached to the ground. I use these landscaping spikes, which are the ones I found were I think 12 inches long, about 30 centimeters, and you can see the tops of them here. So far these ground spikes have been sufficient to hold the fixture to the earth. Again, there's not much loading. I thought if I had to, I could use spiral ground anchors or weights to further fasten the fixture. The final step was to trim all the vertical elements. First, I'll show you the frequency sweep parameters. I go from 11 megahertz below 20 meters to 31 megahertz above 10 meters. And I have 1,000 frequency sample points. If you look at this line graph, you'll see that the antenna resonates at 3 different frequencies corresponding to those 3 vertical elements for the 3 bands. The green boxes here show the bands that we are interested in and their limits. And again, these were drawn by me over the slide. The software doesn't draw these. So this picture is actually the result after trimming. Again, I didn't think of taking a screenshot when I first started, but I can say that when I first started, it looked like this, but these things were just too far to the left. So I needed to shorten the elements, which is what I expected to do. And as I shortened the elements, things moved to the right. I did this in parallel, sort of for all 3 bands. I would shorten this one and this one and this one and keep moving back and forth. I did that because I was worried about interaction between these elements as I tuned it. But I don't think that was that significant. So I have markers here for the edges of each band. If you look at the SWR numbers on these, they are all pretty good, but there's one outlier for the top of 10 meters, and you'll see it corresponds to this point. SWR is slightly above 4, which wouldn't work for me with my radio. Now, if you look at these graphs, you'll notice that 10 meters has the widest frequency range, and it also has the narrowest resonance curve. So that sort of works against us. Now, it turns out that I'm really mostly interested in the lower portion of 10 meters. So this portion out here on the far right, I wouldn't be using anytime soon. So my focus was the lower portion. I could actually shorten that element a little bit more and center it more in this portion and get lower SWR, but I'm actually a little bit more interested in the lower portion of this low portion. So this is fine for me right now. I want to say a few words about antenna impedance. As previously discussed, the impedance of an ideal vertical is 36 ohms. The resonant impedances we see here are about 65 ohms for 20 meters, 43 ohms for 15, and 42 ohms for 10. That implies some ground loss resistance, and that's reality. But it's worse at 20 meters. And the reason for that might be that as you go lower in frequency, you need longer radials. And perhaps my radials are not quite long enough for 20 meters. Another thing is that in circuit theory, lower power loss means a sharper frequency response. And that might explain why the response area for 10 meters is so much narrower than, for example, for 20 meters. So you might think if we had more power loss here, that would widen the response, and it might, but you don't really want to widen your response in that way by introducing loss. Instead, what we would prefer is to use a tuner here probably to get a better match across all of 10 meters. One final thing I wanted to mention is these squiggles on the 20-meter curve. I don't know what causes them, but I wonder whether they are due to the metal window screen or maybe the gutter that the 20-meter vertical element lies next to. Whenever you build something, you are always thinking of ways to improve it. Here are some ideas I had. One is to add more radials to try to bring impedance down, especially for 20 meters. That would make the antenna more efficient, meaning more radiated power. Another idea is to add elements for 17 meters and 12 meters. The length of these elements would be suitable for my setup. I do wonder whether this would be pushing it too far for a fan. In other words, whether interaction between elements would become a problem. Or I could put a tuner at the base and use that to get to the other bands. But then you might say, well, why not just go to a single vertical element and use a tuner for all of the bands? I don't know. That's something I'd like to try. Another thing is, how could I get on 40 meters? Now, I could try the tuner. I'm not sure how well that would work with the length of my elements. Another possibility is that at the end of the 20-meter element, add a trap and a whip radiator that extends above the roofline. I think I could get it to resonate for 40 meters. Now I do wonder if that would have some detrimental effect on 20-meter operation. Finally, I could experiment with the 10-meter radiator to improve bandwidth, to get it to cover more of the 10-meter band. One idea is to use a cage dipole concept, which is where you have multiple wires running in parallel to make the radiator have an effective larger diameter. This is because larger diameter radiators have higher bandwidth. So that's it, and thanks for watching. I hope you found this video useful. I have a couple concluding remarks. One is that antennas are an area where homebrew can be very beneficial, especially when stealth is needed. And also, tools like nanoVNA and Whisper digital mode are great aids for the design and evaluation of antennas. So 73, everyone.